Okay, good afternoon. I'll start the class now. So now in this class, we start looking at the problem-based this one. So next two weeks we will look at that. Okay, means what are the 10 days next 10 days class. Okay, we look at that. Okay, problems. Okay, and means basically the course is going to have a very limited this one, and also we have a limited problems. So we will solve some of the things. Okay. So now the basic thing, the important thing that you have to know is okay in this one. If I am going to keep the your Petard study tube in the flow, okay, or okay. So you know how to calculate your P naught, delta P, as well as P static and your velocity. You know or not? Any question on calculating this one for an incompressible flow? Please, if you don't know, please tell me. Then I can explain to you. Otherwise, I skip this one. Please open your mouth. Excuse me. Any difficulty on that?
No, sir.
All of you are okay?
Okay, sir.
So we know that P naught is equal to P plus half rho V square. Okay. So from these, if you are going to take a P naught minus P, that's going to be made for your half rho V square. This is nothing but your dynamic pressure. Okay. So and also the dynamic pressure, what we call it as, okay, this is okay, your P naught and P, we will be taking it as a delta P. So that's going to be related to your manometric height, rho G, your delta H. This is going to be a manometric liquid. For example, if you take a water, okay. So using these, okay, you can, first thing is, if you calculate your delta P, whether from these one, okay, you can calculate your velocity of the your fluid stream. Okay, let us take it as a air. So you can calculate, okay, P is equal to square root of 2 times rho water G delta H divided by your rho A. So this is what we use to get the your velocity and all. So on same way, what we can do is, okay, if you know the delta P, and if you assume it as, okay, your manometer and all, if you are going to open to atmosphere, what we can do, okay, one end is, if I am going to connect it to your P naught, okay, another end, if it is open to atmosphere, okay, P atmosphere, automatically what happen, I can calculate why your P naught is going to be delta P plus P atmosphere. So I can calculate my stagnation pressure. And same way, I can calculate my static pressure if I open your P, this one instead of P static, if you connect it to YouTube and open to atmosphere, okay, the change in delta P is nothing but, okay, your rho G delta H, okay, using that you can calculate your delta P, okay, P naught P minus delta P, depending on the, okay, how much it's going to have a changes in your delta H variation, okay, whether this side or that side, reverse of that, okay, your sign will change, this sign will change. So using this, you can measure your stagnation pressure, dynamic pressure, and your static pressure, and you can calculate your velocity. If you have a, people are going to give, if they are going to say, if I am going to give a Petard static tube, you should be in a position to find out, okay, all those things. So same way, you need to know about your P naught by P, T naught by T, rho naught by rho. Using these, how are you going to get if they are going to give for a particular altitude, if they are going to give a PA, TA and rho A, you should be in a position to calculate your P naught, T naught, that is your stagnation pressure, stagnation conditions. That and all you can do that. So even rho A is nothing but we know that PA by RTA, R is your R bar divided by molecular weight of the gas. R bar is the universal gas constant. Whether you are going to use molar based or kg based, accordingly you have to use your molecular weight also. Whether if it is a gram, you have to use it in the gram format, or if it is in the molar format, you have to use the molar format. And also you need to know your characteristic Mach number, how it is going to change for that one. You need to know your characteristic Mach number. Now we have seen that for example, any one of you, can you give the solution for that? You told you know about that. I'm going to give your free stream condition, P infinity, T infinity and rho infinity and your U infinity. Somewhere in the top of the location or near to this location, I want to find out your ratio of, let us take a condition between U1, P1, T1 and rho 1. Can you get a ratio between your U infinity by U1? Any one of you, can you work it out and tell me? All of you work out and tell me the answer for this one. I'm going to keep the flow, aerofoil in the flow. It's going to be at the U infinity. These are the free stream conditions. In the somewhere section, assume it as your flow losses is going to be neglected. So can you do that? The flow is incompressible flow. Treat that as an incompressible flow. Can you do this one? I need an answer from you people. If you couldn't tell me, then I look into that. Work it out. These are standard questions for your government exam preparation. GATE or any competitive exam, they used to ask these data questions. I told straight away, but there they will put a Cheska Maska and they will give a lengthy paragraph, and if you are going to deduce it, you are going to get a simplified problem like that. You have to find out your U infinity by U1. I think you can do it very easily. Sanjay, it's nothing to do with the critical velocity, Sanjay. U1 is not a critical velocity, just it's a velocity. Here in the aerofoil, we won't talk about that in terms of critical velocity. When the Mach number is reached 1, then only we talked about the critical velocity. Here we talked about that in terms of critical Mach number. The critical Mach number is the free stream Mach number at which your flow reaches the Mach number 1 at somewhere in the aerofoil section. That's a critical Mach number. I told about incompressible form.
Sir, you told the flow is incompressible, but you have written rho 1 and rho naught.
Yeah, you can take it as rho infinity is equal to rho 1.
Okay, sir. Okay.
That you can tell, sir, while solving your problems. My first semester MTech course, I took a paper on Introduction to Aerodynamics in IIT Kanpur. This is one of the first. But if you solve at the end, it's nothing. Quick, sir. Quick, sir. You can do it.
Sir, I put it in the chat box, sir. Can you check, sir?
1 minute, sir. Yeah, wait for others, sir. Give 5 minutes time for others. Sir, you work it out. Don't think that okay, you have done a correct one. So whether even if you have done correctly, just verify with that. See, few things you have to understand here. Okay, so your P naught is equal to P plus half rho V square. So I told you there is no losses. Okay, and also while deriving your Bernoulli's equation, okay, for the Bernoulli's equation, okay, we used to set each and every condition. So I didn't mention that okay, there is going to be a along the streamline or I didn't mention that. If I mention along the streamline, then you have to follow accordingly. Okay, so any point between any 2 points in the flow. So then what we can do? Okay, P naught is going to be constant. Your P infinity plus half rho V infinity square is equal to P1 plus half rho V1 square. So what we can write it as, okay, in terms of, we want to write it in terms of your okay, we can write any form, it's okay, u infinity by u, okay, as a velocity ratio. V infinity minus V1 is equal to half rho V infinity square, sorry, rho V1 square, half rho V infinity square. Okay, let us take a half rho V infinity square. I can write V1 square divided by V infinity square minus 1. So we want something in terms of V1 square divided by, or okay, let us take a u, keep it as a u. I keep it as a u. It's not a problem. So u1 square by u infinity square is equal to 2 times V infinity minus V1 divided by rho V infinity square, okay, plus 1. Is it right?
Yes, sir. Yes.
So we can write it as rho V infinity square plus 2 times V infinity, or otherwise as such we can keep it. That is 1 plus 2 into V infinity minus V1 divided by rho V infinity square. You can get the velocity ratio u1 square by u infinity square. So if you are going to take a root of that, your u1 by u infinity is going to be square of, okay, 1 plus 2 times V infinity minus V1 divided by rho V infinity square. So rho u infinity square. Any questions, sir? So now what you can do is you go and look at the momentum equation. Okay, people are going to be, okay, derived from the, okay, the main thing that your sorry, yeah, from your Euler equations only we are going to derive that your Bernoulli's form. Okay, so there your case, okay, along a streamline. Okay, what is the form and you are between any point on the flow. So this is the one. So just to keep those relations. Okay, so try to get something on that. Okay, any questions, just to go through that. If you have any questions, please tell me. Quick, sir, I need to go for next one. Any question?
No, sir.
So now what we have done, okay, we have seen for a case of a incompressible flow. Now I told you, okay, in the case of a compressibility, so now in all cases we are going to define a parameter. Here afterwards we will put your dynamic pressure. Already I mentioned about that, okay, your dynamic pressure. We'll be taking it as a Q, that will be half rho V square. So this half rho V square, I can write it as, okay, numerator and denominator I am going to multiply by gamma P, rho V square. So I can write gamma P by rho as a gamma P by 2. This one I can write it as a 1 by A square and V square. We can write A square, V square by A as a Mach number square. Your gamma P M square by your this one. Okay. So your Q is equal to, in addition to half rho V square, we are going to denote, okay, gamma P M square by. So even if you want to know your P is equal to nothing but, okay, your 2Q divided by gamma M square. So now what happens is, okay, sometimes, okay, we can get your P naught using your Pittard study. What are we going to do? We are going to have your P naught by P, okay, is equal to 1 plus gamma minus 1 by 2 M infinity square to the power of gamma by gamma minus 1. So now here, if you want to measure your P naught, okay, if you are going to measure your P naught, okay. So how will you measure your P naught here? Okay. So now your P naught is equal to P into, okay, 1 plus gamma minus 1 by 2 M infinity square to the power of gamma by gamma minus 1. So next what I am going to do, okay, I am going to subtract the P both side, okay. I am going to take the your plus 1 and minus 1. Or I am going to both of the side I am going to subtract with the P alone. Okay, so now we can rearrange this, okay, your P as a 2Q, already we proved that, okay. So your P naught minus P is equal to 2Q by gamma M square into 1 plus this one. So now, okay, for gamma is equal to 1.4, let us take an air standard condition, okay. let us have a simple assumption of gamma is equal to 1.4 or 7 by 5. Okay, 7 by 5. If you substitute it here, okay, P naught minus P is equal to 2q gamma m square. I'm going to get, okay, 1 plus m square by 5, 7 by 2. To the power of 7 by minus 1. So using Taylor series, okay, your binomial expansion, okay, if you are going to rearrange that, okay, you are going to get P naught minus P is equal to Q into 1 plus m square by 4 and m to the power 4 by 40. So higher order terms we are going to ignore it. Okay. So now what will happen? Your m is equal to 0. That's going to matches the your what happens? Your matches your incompressible form. When I put a m is equal to 0 or 0.3, it's going to be close to that. Your P naught minus P is equal to Q. Something close to that. Okay, it's going to be nothing but okay your incompressible form of okay. Your m is going to be somewhere near to 0. Okay, between up to 0.3 also you can put it. Okay, it's going to satisfy the incompressible form. So here we are going to denote a parameter called K. That's going to be P naught by P. So your Q is equal to P naught by P. P naught minus P is equal to your K. So your K is nothing but okay. Your from here, okay, K is equal to nothing but your 1 plus m square by 4 plus m square m to the power 4 by 40. So now already I had given this problem to you. Okay. Let us take a condition of okay free stream Mach number of okay a free stream Mach number m is equal to 1.8. Let us take it as your P infinity as well as T infinity. Let us take it as a standard sea level condition. That is 101325 into 10 to the power 5 Newton per meter square. And let us take a T infinity as a 288 Kelvin. Can you estimate what is the if I am going to treat the flow as a incompressible, what is the possible error? Can you estimate and tell me? So now, okay, you can find out your K. Okay, from this you can go ahead further. Try with that. If you want, I can explain the procedure. Find out the K value using the Mach number. Okay. Find out the P naught value from that one. find out the Q compressible, okay, is equal to P naught minus P by K. K, okay, you are going to have a where K is equal to 1 plus M square by 4 plus M to the power 4 by 40, okay, using that estimate the value of K. Now, okay, here your P naught is, okay, you find out that your P into 1 plus, because assume that, okay, flow is going to be an isotropic flow, M infinity square, okay, to the power of gamma by gamma minus 1. This is your P infinity, this is your P naught. You know the P infinity value, you can get the P naught, substitute it here, you can get your compressible. Q incompressible, if you are going to treat that, okay, K is going to be 1, okay, so it's going to be P naught minus P. See the, okay, percentage error, okay, how much the percentage error? Q compressible minus Q incompressible divided by Q compressible into 100. That's one is going to talk about that your error. Find out that. Or otherwise, okay, don't consider this part, okay, don't consider. Using a compressible relation, you know the K value, oh, but you don't know the dynamic pressure value, then only you can, yeah, use this one, okay, use this one, get the P. Sasang, I need an answer for this question from you. Sasang. Sasang, are you there? Sasang, are you there? Quick, sir, I need an answer. Have you got the answer? Sir, how much time it's going to take?
Sir, is it minus 1.07%?
Check it once again, sir. Others, please check and tell me. Sasang, I need an answer from you.
Sir, is it minus 107.2?
Minus 10
7.24, sir.
107%, or are you talking about that? How much you are?
Yeah, yes, sir. Minus 107.24%.
He's giving you some other answer. Sanjeev,
Sir, I also gave the same answer, sir, but I thought no one will have 100% error, so I just
Yeah.
didn't multiply by 100.
okay. But you look at the MAC number, sir, 1.8. Whether it's in compressible regime or incompressible regime.
Compressible.
Then check, sir. Check once again, sir. Anyone else? Kevin, Sanjay. Oh, sorry. I made a mistake, small mistake. Sir, 101325 Newton per meter square, not into 10 to the power 5. Or you take it as 1 atmosphere. Okay, Now I'm going to give a task to you. You take a sea level condition, okay. I'm going to keep a flow, okay, m infinity as a 0.3 and a case of m infinity as again as a case of 2.1. Okay, your P infinity is going to be 1 atmosphere and your T infinity is going to be 288 Kelvin. Can you tell me, okay, what is the possible percentage of error? If you are going to treat the flow as an incompressible, okay, if you treat the flow as an incompressible, okay, what is the possible error? You know the relation now, okay. If you want, you can take a screenshot for that, this relation right now, or otherwise refer Radhakrishnan book, okay. Instrumentation measurement in experiments flow rates, okay. Now the time is 2:50, okay. I want to see this assignment, 29 assignments within what is it? It's 3 o'clock. Within 4 p.m. in my team speech. If you are not going to submit it, okay, I'll reduce the mark for your internal accordingly. Please inform to your group. Okay, that's all the things I want to say in this class. Okay, right now. And also another one more thing. Last year GATE examination question paper accidentally I gone through completely. So it seems to be if you had studied your 6th semester until 6th semester properly, surely you could have got a rank within 100. Anyway, past is past. We look at that. Sanjay, are you there? Sanjay, are you there? Sanjay,
He's having some net.
okay. Okay. Anyway, no problem, sir. No problem. Whatever the question you have shared to me, that is one is okay, related to your shadow graph. Whatever the, if you had attended the GATE paper, okay, with a single mirror, okay, how the gradients are changing and all, that is your shadow graph technique. And also they kept a wedge in the supersonic flow, and then they asked you to 4 choice they had given. They asked you to pick up which are the correct, multiple selection correct answer. Anyway, okay. Maybe to next class we talk about the Rayleigh's formula, Rayleigh's method formula. We solve problems based on that, and also we spend some more time on estimating a Mach number in the supersonic tunnels and your static pressure, stagnation pressure, and all. Okay. We look at the techniques in the next class. Then afterwards we go to subsonic tunnel. Then we look at the uncertainty. Okay. These are the things we have to look at that in terms of problem aspect. Okay. Yeah. Any other things? Anything else?